Okay. Let's get started here. And you know, when people think, let's say in media about data science, I came by today and I had a guy in my office who's, a researcher at a national lab someplace, and he says, "Oh yes, we're doing data science, but of course it doesn't mean what you guys think it means," and stuff like that. Data science is a buzzword. Big data is a buzzword. And, and these are buzzwords that have kind of gotten, I think, conflated in the popular consciousness a lot. But this idea of big data is an idea that probably hit the popular media, I will say now, about 5 years ago. Maybe it's less, 5-ish years ago, which suddenly said that somehow data sets had gotten so much bigger that there was a new sense of scale. As you had a new sense of scale, it created wildly different problems and wildly different possibilities. And as I think about big data, I think about trying to analyze data sets, that involve things like all of Twitter, all of Facebook. Okay, if you're Google, you're analyzing, all of the web. Okay, if you're doing genomics these days, medical genomics is now to the point where there are full genome sequences on thousands of people. Now, what does that mean? Well, a genome sequence involves 3 billion bases of information. So when you start having that on thousands of people or tens of thousands or eventually on everybody in the universe, you're starting to talk about problems that are on a scale that are much bigger than we dealt with. These days Flickr is probably not the big photo site, but if you're on Instagram or something like that, then you have a world where you're getting millions of images a day, and and working with all this data is kind of involves a lot of the stuff that we talked about in here, but it also, in general, problems get harder as the size gets harder. Okay, any questions about that? That should be self-evident. In general, the way I would put it is that the difference between big data and little data is size. That's obviously my first observation. But in general, the kind of mistakes that people make with big data, a lot of that are mistakes you make with little data. That's why I kind of pushed this part of the course off till the last, like only 1 or 2 lectures on it. But there are logistical differences when it comes to working with very large data volumes. I did want to talk about that a little bit. Any questions? Okay. So when people talk about big data, how big is big? These are numbers that change all the time. These are some statistics I took. Last time I taught the course, I took these statistics. I didn't bother to update them. But they are, wildly, they are big numbers. So Apple has 50,000 app downloads a minute. And you know that they are keeping track of every, obviously for billing purposes, they've got to keep track of everything. For data purposes, what are the most popular apps? What kind of people are downloading what apps? You know that there is a lot of data there, and you know that there are a lot of people that are analyzing it. If you think about what Google is doing, when I looked at this, 2 million search queries per minute. That means that not only do they have to log this for future use and analyze, they've actually got to serve the queries, and they're serving that over the entire web search. When I took a look at Twitter, was at this point about 500 million tweets a day. I think this presumably has gone up in the last 3 years. Okay, but there are applications that have to deal with this kind of volume of data, and it requires a different set of tools than we would be dealing with otherwise. Any questions? Okay. Actually, for any of your projects, what is the biggest data that we have seen in here? Okay. Does anybody on their project proud of some scale of data that they have? Okay. What? Scale is what big means is different. Is different. Obviously, when you were in the Middle Ages, big data meant having a book. Okay? But what's the biggest data set people are playing around with in here? What? 5 gigabytes. You're saying 5 gigabytes. Okay. Saying you find something difficult with 5 gigabytes.
Yes, it's about the way, it's not just about the size of it, it's about the way it's arranged and the way it's presented and the way it changes. So that's why I call, even though it's not big data in terms of size, but in terms of its velocity, in terms of how it's...
Okay, we haven't talked about what these things mean, but you're telling me 5 gigabytes. Who else? Which data set was that? That was the Okay, that's small. Anybody else have a big data set they're doing for their project that was reasonably big? I'd say the city bike data was probably one of the bigger ones. How big is this?
City bike was about 1 gig per month.
1 gigabyte per month, okay? And is 1 gigabyte per month big? Well, you could say that's every bicycle movement in the city of New York.
Per month plus you had to analyze it over a year, so it makes it
12 gigabytes, okay? So is that a lot of data or a little data? I don't know if we can take a vote here. Again, there's a relative thing to think about it. On some scales, that might be a large amount. On another scales, if you think about it, that's nothing. What is one way to interpret 12 gigabytes as nothing? Okay? If I go to the hardware store and I buy a disk drive, how much can I buy? How much has anybody bought a disk drive for their machine recently? Or a hard disk or a separate storage thing? No, okay. Last time I did, I think I bought a 2 terabyte disk because I'm cheap, and I paid $100 for it, right? So by that definition, what is 13 gigabytes of data? It's what sits on, it's nothing. Does everybody agree? Okay. There's one of my favorite words in Yiddish. Okay, Yiddish is a language. It is a very expressive language. I don't know how many native Yiddish speakers we have in this classroom. Actually, I think I do know. But there's a word called bupkis, which I always liked. And bupkis is a word for a quantity that is too small to matter. Okay? So if we take a look at that, when you heard that Donald Trump turned down the president's salary, okay, what is your reaction supposed to be? That's bupkis, okay? I mean, it's a quantity that is too small to matter to him. What are they paying you as graduate research assistants? Bupkis, okay? Any questions, okay? But the way I think about big data, the data size issue, is that there is big data and there is bupkis. And just about everything we have dealt with this semester has been bupkis, okay? In that you got, how much data did you get, the railroad people? What's the size of what you were working with? 200,000 what? Records? Bupkis, okay? I mean, if you stored it on a disk, you're easily talking about $2-3 worth of disk storage, okay, for everything. Does everybody kind of get that idea? So there is a difference in scale between the kind of things that typically these big logging companies are, big companies that have a lot of logging or a lot, where they have sensors that are doing logging or, online services serving zillions of customers do, okay? And one has to kind of respect what the differences are. Any questions about that? Yeah.
So this is storage is in two senses, right? Like storage is also what you can have in memory, right? Like that is not in scale of terabytes. That is still in gigabytes. Like if you have a laptop, you won't be able to like put it to memory at a time.
Okay, so there's a question of what is big, I guess, if we want to talk about this more seriously. And one notion of big is that I guess the first thing is something becomes big the moment the algorithm you want to run on it is too slow. Okay? So arguably we can say that some of you, some matrix things you guys may have wanted to do on your data might be already that's too big. Okay? Then there's this question of what sits in main memory on your machine. And you're saying, oh my God, look, this my laptop has, much space does your laptop have? 8 gigabytes. And look, I can't hold that all the city byte data from New York City in main memory. Okay, does that make that big? So what should be clear is that as things get bigger, things get to be technically more difficult to deal with. That's, I guess, the thing. Why did you care about it sitting in main memory? Well, maybe because it's faster, maybe because it's easier to write such a script and stuff like that. Once you can't get it on main memory, now it's in your disk, and that's a notion of big. And once you fill up your disk, what's the next notion of big? Probably you want to start talking about multiple different computers, right? And now you're starting to talk about clusters and networks of machines, okay? And so there's different notions of where big starts. To my mind, the kind of big thing that I would say is when you start needing more than one computer to analyze it, now you are in the realm of starting to get big. That would be my definition of things, okay? And it's clear that the people who run these things all have huge networks of computers to deal with what it is. It isn't just dumb storage. It's, to do the kind of processing and stuff like that. Any questions? Okay. So you had mentioned something, what about data velocity and stuff like that? When people talk about what you call big data, by people meaning the management types that write books about how you should what you should worry about in industry, they sometimes describe 3 V's of big data, where one of it, the obvious one, is volumes, that, as you get, larger and larger things, you've got a data set that is larger and larger is more complicated. Volume is one aspect of it. And most of our projects in here have sat at the, I will say, gigabyte level. That seems to be about where people are. Okay, but obviously there's a large amount going beyond that. Another dimension for talking about data is velocity, which is a question of how often it changes and how often it's updated. And, most of the projects in here deal with what I would call batch data, where the data is, you're downloading a snapshot of what the data was at a certain point, and then you're going to walk away and leave it. With the possible exception of the city bike people, they were living in a batch world. Everybody here should be living in, I suspect, a batch world. But there are questions of, as you start often in certain domains, you need to be dealing with data in real time, okay? And in order to deal with large amounts of data in real time, you need a different level of architecture and, representation and algorithm to deal with that. Any questions? The third V that these people talk about is that often what is considered to be big data has a lot of variety. In an ideal world, most of you have, basically CSV files or spreadsheets where everything is a nice column. Everything, you have a column. You know what the columns are. You have a lot of rows, probably not that many columns. But in many, let's say, modern data applications, one of the things that makes it harder to do is the fact that you have multiple different types of things to deal with. If you are Facebook, what do you have? You have, obviously you have text people write. You have network interactions between who's clicking on what and stuff like that. You have people posting videos and photos and things like this. And so if you are Facebook, you are dealing with analyzing a complex data variety that's not very well structured, okay? And this is one of the things that makes it very, very challenging. Any questions? There's a fourth V that people sometimes talk about called veracity, which is a question of how much do you trust your data. And in many cases, there is a problem. This is actually a problem in many of these kind of applications. Which of these applications have trouble with trusting where their data comes from or the quality of their data if you're using it for certain kinds of things? Twitter. What about Twitter?
You could generate a bot. You could create a bot to create messages.
So one problem with Twitter, of course, is that it's very easy to write bots that write things, okay? So a large fraction of these 500 million tweets are written not by people, but by bots, okay? And so if you want to try to analyze the Twitter stream and understand what it's thinking, well, if 80% of it was written by bots, then you've got a problem, right? Most of it is not really, you've got to, there's a spam problem there. Does everybody kind of see that? Now, if you're the Library of Congress, you probably have less of a spam problem, right? You're dealing with books and things like that. So there is a difference between things that it knows and things it doesn't know. Any question about that? And so a lot of, let's say, the analysis on social media, a lot of it has to deal with veracity problems. You have to figure out which of this data is really worth analyzing and which of it is spam. Any questions?
Like how to deal with it, like veracity, how do you tell whether the data is like correct or not? Like
how do you tell whether the data is correct or not? Well, in your, I guess what I would say is you have some subdivision of effort devoted. You spend a lot of time cleaning things. There is no question that if you're a company like Twitter, you have a lot of people working on spam detection, okay? And you also realize you're probably losing. There's a lot of people trying to spam you and stuff like that. I will say we had a company that was doing social media analysis, and a lot of what we did was try to figure out what was spam and what was not spam, okay? Because we wanted to trust and analyze people's opinions, and so recognize that this is an important part of the problem. If you don't worry about it, then you're going to end up getting junk on it. Any questions?
if you're writing a bot, suppose, to influence the current scenario, like to influence, suppose, the current, who's the most popular presidential candidate, suppose,
Yeah.
write a bot and say that no, Hillary is very popular, right, suppose. So that's not spam, that's something else, like spam and,
Well, so the question is, what is it? Again, right now, obviously, the whole notion of fake news is, as we speak, is a big thing right now in the news. In the media, and the question of what is fake news and what is not fake news. Obviously, Facebook is spending right now taking a certain amount of heat for disseminating a lot of fake news, and what's clear is, you want to be able to detect it, but what is fake news? It's not, it's a hard, first it's hard to define, and second it's hard to detect even once you have defined it, okay? But I guess the point being that if you want to try to analyze social media and get something from it, if you ignore those issues, you're going to get junk for analysis. Any questions? So one person I spoke to once who kind of impressed me, he said that what big data is bad data. That's basically what the story is. That usually when big data comes from, where does big data come from? Usually it is some ambient monitoring of the world, as opposed to data that was collected for a particular problem that you're trying to solve. Okay? So why is it that Facebook has all this people data? It's not that people were trying to give data to Facebook particularly. People were trying to connect to their friends. And does Facebook tell you a lot about who's monitoring, who was liked better, Hillary Clinton or Donald Trump? Probably, somehow, but that wasn't, the purpose why the data was collected. It's not clear that the data was optimally designed for this kind of thing. This is why people have polls. Polls are questions that are, is it a data collection targeted for a specific kind of problem? A lot of these other, when people do laboratory experiments, usually they are trying to collect data targeted to a particular question. One difference with most of these kind of big data applications is a lot of the monitoring is done, you're collecting what you have rather than what you want. And therefore, a lot of the problems of, veracity, what does it mean, is it any good, kind of fall out of that. Okay? Any questions about that? Is Twitter more prone to spamming than email? I doubt that. But email is quite prone to spamming. What fraction of email messages are spam? Well, it depends. I mean, in terms of how much email is flying through the ether, I've heard numbers of 90% of all email is spam. The difference is that your spam filters are pretty good, okay? And the spam filters for Twitter, my guess, are probably less good for a variety of reasons. You know, the kind of economic incentive. You know, the type of spam that you see on email is different than the kind of spam you see on Twitter, right? On email, it's always trying to target you to buy something or to do something. Whereas, you know, what goes on, you know, what comes from a Twitter bot. You know, some Twitter bots are written for amusement, and some Twitter bots are written for political reasons, and it's harder to see what's going on there. Any questions? Okay? So these are the things you have to worry about when you are trying to analyze a big, modern, complicated data set. Any questions? Okay. So on all of the projects that we, again, as far as I can tell, everybody here, the amount of data that they're working on for their project is bupkis. For any of the challenges here, were there large data sources that maybe if you, by some miracle, had access to, could have been helpful for you on this? Okay? Can anybody look at any of these things and say, you know, gee, yeah. Snow on Christmas, you have access to all the weather data for every place for years. Is that big data or not so big data?
Oh, well, big data means ambient data.
Well,
but if it means big, sure.
Well, it depends what big is, but I mean, how big would this be? Let's say that how many stations are there in the United States, weather stations, if they're on the order of thousands of them?
Well, you have multiple readings per day. You'd also imagine it's not just temperature, there's humidity, wind speed. Could be talking 5 to 6 numbers per recording, per...
So it's a question of how much data is there really. I would say historically, as taken by the old man at the weather station going out in the cold and looking at the thermometer, okay, the answer is there isn't, you know, there's a lot of it by some scale, but do you need more than one computer to try to analyze that? Probably not. Now, if we are in a world of weather satellites and things like this, now we can kind of imagine a world where these things are constantly beaming images at us, okay? If you've got a real-time measurements on a temperature sensor, okay, or a wind speed sensor, now you're starting to talk about something that can gather large volumes of information. Yeah?
Are you asking if this snow on Christmas could be a big data problem?
Yeah, that's basically what I'm asking about.
If you use satellite imagery, then absolutely.
If you use satellite imagery, I think that that's basically right. Okay, so satellite imagery, when you start talking about real-time streams of video from enough different places, now you're talking about larger data. But it's hard for me to keep track of this. Would a real-time camera, one camera monitoring the world, is that something that any computer would have a hard time keeping track of?
I mean, considering it depends on if you have thousands and thousands of images to analyze, and then you differentiate between those images and then detect temperature.
You know, again, maybe. But again, I do believe that, do meteorologists use a lot of data and analyze a lot of data? The answer is yes. But a lot of that, by the way, is computed data, simulated data. There's certain raw numbers that come in. They're very complicated simulations and stuff that come out. So there's a difference between, you know, what I would say is the computational result, which is going to be, is it raining? Going to rain tomorrow, which is 1 bit, okay, from all the intermediate products that are there. Any other of these that look like they're things that you, what? Future gold and oil prices. And again, it depends upon here. Is there a lot of data on that? I would say it depends upon, again, at what scale, what time resolution you're measuring it on. Historically, if you measured the price of gold every day or the price of oil every day, there's not much there. Now, if you analyze every transaction that happened on the stock, stock exchange, okay, every time a share of a particular mining company traded, okay, or whether there was a futures contract or something like that.
Instead of looking at the
So you're saying if you looked at the order book, okay, meaning how many people bid for what at what price for 70 or 80 years, that would be large. But of course you don't have it for 70 or 80 years because they haven't been keeping track of, of those kind of records. But it is clear that in monitoring, financial transactions, there's enough financial transactions in the world that are happening hundreds or thousands of times a second, that starts to add up. That much we agree. Baby weight? Well, how much data would there be on baby weight? Okay? What? You say so many babies born. How many babies have been born? Okay? I mean, if I want to take a look at, is this a lot of data? First of all, if we could get it, is that a lot of data? How many? No, it's only been, how many people have been born in this world? 10 billion? I mean, there's 7 billion alive. All of them had to be born, but there are plenty of dead ones. Is it 100 billion? 100 billion records of how much they weighed. Would that be a lot of data? That might very well fit on the $100 disk drive that you would buy at the store. Oh.
It's not just their baby weight, it's all the factors that determine baby weight.
Okay, so the answer would be if you had a complete health record of everybody in the United States, yes, you're talking about serious stuff, okay? And, of course, who has that data? That's probably a good example of data that nobody really has, okay? And that part of the trickiness is often with several things. Data that you would want, it's spread out over many, many different sources. There isn't a central place for it. There are privacy issues in getting it. There's a lot of different things, right? It is clear that, in an ideal world, all the medical records would be in a central place where you could analyze it, I think, if you ignore privacy issues, if you ignore certain other societal problems. Any questions? Okay, any of these other ones? People think there's a lot of data on little data? Okay, so recognize still, unless you are really talking about constant, high-speed monitoring of things, the amount of data you see is often substantially less than you would think. Any questions? Okay? And again, so what do you do with this data once we have it? Well, we talked about machine learning. And, again, in general, I'm not going to talk too much about machine learning on a very large scale, except to sort of emphasize that if you have models that have very, very few parameters, you can't possibly benefit from a large number of examples. Okay? So in some sense, what made deep learning an interesting thing was that it had, it is a model that is capable of having a large number of parameters. So if you are in a world where you have, where you do have that scale of data, then things start to get interesting. The other thing that should be clear is that, that algorithms that run on large data have to be near linear to run, okay? If you have an algorithm on billions, I'm scoffing at 100 billion records, but of course if you have to do a pairwise comparison of each baby against each other baby, this would be a hopeless task, okay? So algorithmic complexity must be linear, or sometimes there's now a growing need for sublinear algorithms. What would a sublinear algorithm be? Log n, which if you start to think of it, what does a sublinear mean? It means don't look at all the data, okay? Which seems like a hard thing to think about in the first. How can you have a sublinear algorithm, okay? That doesn't, that processes your data without ever actually looking at it, okay? But we'll go through what this kind of thing. How can you have a sublinear algorithm? What? Sampling, okay? So one of the most important things that you can do with big data is throw it out. This is actually one of the big wins that you have with a large data set, is that if you have enough data on it, you can afford to throw a lot of it away to make your analysis easier. Does this kind of see? There's distinguish between filtering and sampling as two kind of related ideas. Filtering is the idea of, on a application-specific thing, okay, identifying quickly which records are of interest to you and which ones aren't, and then throwing away the ones that aren't. Okay? So for example, if I was going to try to train a language model on Twitter, quite often a thing you might want to do in, say, gee, if I had all the tweets, could I build a model for helping to analyze sentiment analysis? Out of a tweet's going to be a happy tweet or a sad tweet. Well, there are 5 million tweets, I said 500 million tweets a day, which means that if you pay for the tweets, you can get 500 million a day. If you don't, you can get like 1% of them for free. That's 5 million a day. That's still a fairly large number. Recognize that if you wanted to build a language model, one of the good things is that you can throw away all the ones that aren't written in English, okay? And it will still leave you with, if only a third of the tweets, okay, are in English, if you throw them away, you still have, the non-English ones, you still have about 1.5 million tweets a day, even if you're not paying. Does everybody get that idea? So one thing that's kind of important is that if you have big data, one property you have is that you can discard the stuff that is harder to interpret, okay, and less clean and less good, and focus on the better stuff. Any questions about that?
It's like reducing itself rather than using log and something like that.
Yeah, so this is sort of an initial pass of just using, this is using your, what I would say, this is an application kind of specific idea. You should kind of say, oh my God, I've got so much data, how do I analyze it all? But what is the stuff that is most relevant to me? And this is usually a smaller thing. And if it's smaller, you can get, you have certain wins. It's easier to work with. Okay, it's more on tune. Any questions? Okay, that should be obvious. There's another notion of sampling data, okay, which I want to talk about, which has to do with even if all the data is good and relevant, okay, it often pays to throw some of it away, okay, or at least partition it into different chunks, which you might do different things with, okay? So, for example, suppose I have, again, if we talked here about learning thing, if I wanted to train a regression model to predict, something from, let's say, what were we going to say? Let's say the city bike data. How many rows of city bike data did you have? How many bike trips were there? I'm looking here. Does anybody know? A month?
No, years. The data was from 2013.
2013 to there. How many rows were there? How many trips were there?
They gave it by month.
And how much per month? You don't know, but I mean, I'm going to just take a guess that you've got 100 million trips there or something like that in the data. Recognize if you're building a regression model, how many dimensions did you have on the data? 8 to 10. Okay, if you're building any kind of a regression model to fit a 10-dimensional thing, you have wildly more records than you need. Does everybody kind of see that? So it might very well pay to, to sample it and reduce it to a smaller amount so that it's faster to work with and understanding it. Any questions?
So when you say reduce to a smaller amount, you mean everyday trip, you can just take like weekly trips or monthly trips?
Well, let's think what you would do. That's a good question. Suppose you wanted to get, take the data set coming from all of Citigroup and make it smaller. How would you make it smaller in a way that will still enable you to answer as many questions as possible on it? Let's think about that. Yeah?
Well, just for one thing you don't want to do, right, is you don't want to just take the month of April or the month of December. You have to sample evenly across time.
Right. Right. So one bad thing would be to take 1 month and say this represents all of what's going on there, because probably what you've got is a lot of detail about a period of time. Who knows what happened in April? If it was a nice month in April, you have a wildly different characteristic than you had all year round. Okay? So for many questions, if you wanted to deal with it, I would probably be interested in a lower resolution data over a larger period of time. Yeah?
Like data reduction of term code, SVM, maybe something like that.
What?
To reduce the number of dimensions, like still retaining the things.
Well, it's a question of, when you talk about it, sort of like if we were doing some kind of SVD, right? Or some kind of way of reducing the dimensionality. Here, notice that with the data we're talking about, typically, it's not that we've got a large number of features on a modest number of records. That's where a data compression would normally be good, right? Because if all the features are correlated, if we did an SVD, that's what you would hope to compress. Instead, we've got a huge number of rows and a smaller number of features, right? So it doesn't quite lend itself into the same way, okay? How might we do sampling here? Okay, yeah.
Collapsing it by time would be a good idea, right? Every day you have 24 hours, so you can just visualize the data depending on what time of the day it was.
So one possibility, notice that there's a difference here between, one thing you may be saying by collapse it by time, you're saying aggregate totals. You're saying instead of giving me a record for everybody who was on City Bike, you're telling me saying that in this hour there were 573 people who did this. In this hour there were 673.
Maybe I could do that per station.
That's a summarization, but that's not really like sampling. It's not that you're basically started doing aggregation on it. It's not like you're sort of just throwing some of the data away, okay?
So maybe for each year and then for each month and each week we can pick up like 2 weekdays, 1 weekend, and take for every month like 2 weekdays, 1 weekend like that.
Okay, so you're saying sample certain days and stuff like that. Don't know.
Why would you not take them randomly?
Why would you not take them randomly? That's probably what I would kind of like to say. So let's go through ways that you might subsample data. The first one that people usually use is what I would say sampling by truncation. If I'm given a file with 1 billion records on it, and I need 100,000 records on it, one argument is that why don't I just take the first 100,000 records from the file, and that would be my data set. What is bad about that? The order of the records often matters in a file, okay? Often in very mysterious ways. If I took a look, for example, let's say that I had a record of all the people in the United States, okay? And I took the first 100,000 as a sample, okay? If I sorted them by name, what kind of biases would I have there, okay? There are a lot of ethnic biases. Are there any Chinese names that begin with A? I don't know if we have any representatives here. But Chinese names begin with A less often, at least in my experience, than Arab names, Islamic names, okay? And so you could very, very easily get a warped view of the world if you sampled from things where there was, things were sorted lexicographically. Any questions? Temporally, often if you temporally do things, you will get them sorted in a way that, the old data, if you sort them temporally, all you're dealing with is old data. And for many cases, that's not really what you care about. Even if you take the newest data, that's often not what you really care about. You'd like to get some kind of a trend about the whole series. One thing that's kind of funny is even when you sample based on, let's say you sort things based on numbers, okay, you often get ID numbers, you often get biases, okay? So again, you guys now, how many of you have U.S. Social Security numbers? Some of you do, okay? Now, you guys may not know it, but by taking a look at your Social Security number, I can tell you what year you got it from and what state you were from when you had these things, okay? So that in general, the state, the distribution of Social Security numbers is encoded by geographic region. The first 5 digits encode the region and the rough time when you got it, okay? And the last couple of 4 digits are kind of, counters, basically. Once we knew you were in this bucket of people, they basically just count them linearly. So you can often find surprising problems in numerical features. Okay? One thing that I heard was that, that on some Kaggle competition, we were trying to identify healthy people from sick people, or it was a classification problem like that. What they ended up discovering, somebody discovered, was the ID numbers of the records. They had put all the healthy records ahead of all the sick records. And so result then, the position of where you were in the input file decided whether or not you were sick or healthy. Does everybody kind of imagine that? So there's a lot of things that you could encode by numbers and things like that. So if you just do things by truncation, bad things can happen. What's another way we can get samples of things? A better idea is to do random sampling, where let's say you have a zillion records, you have some probability P, and you sample you flip a random number for every record, and with probability P you keep it, otherwise you discard it. Okay? What are the issues with something like that? The good thing, one thing, there are going to, of course, be, whenever you do some sampling, there's going to be some regions that are going to be oversampled just by the nature of the draw, but that's probably something you can't handle with. One problem with random sampling is that it's not really reproducible unless you have the random number generator, okay? And it's often the case that if you take multiple random samples, there's little that's going to be used to keep them disjoint. So you could imagine a world where you have this data that you're training on. You train on a random sample of data. And then you go and pick another random sample as evaluation. What fraction of the random sample data that you use for training will kick into the evaluation part? Well, 1/5. Does everybody or not 1/5, it depends on what that probability is. But does everybody see kind of what the problem is? If you sample data according to, randomly for building different, and you repeatedly sample it, you're often going to get overlapping between that. How can you handle that? Is there any way that you can handle that?
Just check it, like when we get a new sample, then whether that particular ID is there in the...
You might explicitly sample it, okay? So maybe you say you have this big data set you're proud of, you sample it and then remove it, maybe, okay? One other idea that is almost like random sampling, that is solves that problem, would be if you did uniform sampling. Suppose we sampled all records that were congruent, I'm congruent, that are equal, that are congruent to I mod M, okay? So let's say we sampled every we start from the 17th record and sample every 101st record. Does everybody agree that we're going to get 1/101st of the total data there? And if next time I want a different sample, if I now, instead of starting at position 19, I start at position 21, I will get a disjoint set of records. Does everybody kind of see that? So for certain applications, we like random sampling because random sampling gives us theory, and this is good, and in many ways random sampling is a good thing. There are times when this has the property of being quick and reproducible, it ensures disjoint samples. You get exactly as many records as you want. With random sampling, you can't guarantee. Do we prefer random? As with everything else in the universe, it depends, okay? This solves certain problems. One problem, for example, that Twitter does, Twitter will give you access to tweets. They give you like 1% of the tweets you can get for free. How do they do it? Do they give you a random sample of the tweets? Absolutely not. Why? Because if they gave you a random sample of the tweets, what are you going to do if you want more? You're going to get some other buddy and ask for another random sample. And does everybody see that eventually everything would leak out? So what do? They instead will give you, something like I congruent to, to 0 mod n. each tweet gets a number, an ID number as it rolls in, and they only release things according to, every X tweet. Any questions? Okay. So, well, this is a question of when you buy from Twitter. Okay, there are different classes of products, depending upon whether you're going to be getting 1%, 10%, or 100% of the tweet feed. Okay? And again, this is a function of how much money you're willing to pay, right? If you're willing to pay bupkis, okay, this is what you get. Okay? Yes?
Isn't this going to generate the same Twitter tweets data set for everyone?
Isn't that going to develop the same Twitter feed data set for everybody? The answer is yes. And that's exactly what they want for people who aren't paying. Does that make sense? That's the whole point of this kind of a thing, right? So this is, this is one kind of simple sampling mechanism to ensure that everybody who uses this mechanism gets the same data, and nobody gets other data that they might be able to use. Any questions? Okay, good. Now, often in a sampling problem, one other class of sampling problems that are kind of interesting are stream sampling. Often you have, let's say you want to see a random sample of n thing. Let's say you have a stream coming in of items. Like, what would be a stream come? Well, tweets come in, right? You have tweets, 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 tweets. Suppose I want you to give me, to get a random sample of all the tweets for the day. Okay, I want 100 random tweets. How can I do that? Now, one possibility you might say is, well, sure, collect all of them, then randomly pick, if there's n, n is equal to 1 billion, now give me 100 random numbers, integers from 1 to 1 billion, and pick out those tweets. Does everybody see that would give you a random sample? But what's the problem with that? First of all, you have to wait for the entire day, but so if I say I want it now, okay, that becomes harder. What's the other problem? First of all, you have to store the stuff that you really didn't need. Why were you randomly sampling this? Often if you have a sensor coming in or a stream of things, you don't have the ability or the patience to want to store these things. Okay? Okay, so, okay, let's say there are different ways of sampling, but does everybody see kind of what the problem is? Let's say that I have these items. Let's say I only have an array of size k, and I want to get a random sample of the n records. N is big, k is relatively small. I have these records coming by one. I can't store them all till I need the random sample. How can I get a random sample of the records? Do you kind of see what the problem is?
You have a probability of accepting. No, that wouldn't work.
What wouldn't work?
Well, I was thinking like, but if just generate a number between like 0 and 1. If it's higher than the threshold, like accept it or reject it.
Okay, so the question really is, well, you're saying here are these records coming in, and you'd like to make a decision, which ones will I accept as they're going by. Is that kind of what you're saying?
Yeah.
Okay.
Just probability on the whole sample, and if you do the same thing, each event is independent, right? Each tweet is independent, so it should not really matter if you are applying the same probability on the whole set or on each event.
Well, it should be clear. What does it kind of mean? Let's think what it means. If I'm sampling this randomly, what should my probability of acceptance is? I want to have k random, k is here is 3, right? I want 3 random records. When I see my first record, should I accept it?
So you have like a 33% chance of acceptance or something. No, that would, sorry.
Okay, should I accept it? Now, again, if you don't know when your stopping is, a streaming thing is continually here, right? And you want to at some point say, give me a sample of what I've seen so far. Does everybody see that? What's the probability I accept my first record? 1 if I don't know what else is going to be there. Does everybody kind of see that? So I should accept this record. I should accept this record. I should accept that record. Right? Now the fourth record comes in. What should I do with the fourth record if I want a random sample of all the things that come in?
Maybe drop one of the other ones and take that one?
Should I drop one of the other ones and stick this thing in? Well, should I?
How would you know like this one is the one that you want to have?
Well, it should be clear I shouldn't automatically stick it in. Because there's a probability in a random sample, there's a, something like a 1/4 probability this one would not be in there at all, right? What is the way that you can do it? It turns out basically, if I flip a coin on the new record, I have K records, I've put my first K records in. And now the next one comes in with a probability of 3 out of 4, I'm going to want to keep this record. Does everybody kind of agree?
In that you already know the n, right?
I know the n so far. This is the difference here, right? I don't know how many tweets I'm going to have at the time you actually want to look at my random sample. Does everybody kind of see that? Okay. But if instead, what I do know is that if I take this record, there should be a 1 in 4 chance, a 3 over, if n is the number of records so far, there's a 3 in n chance that this record would be part of, the fourth record should be part of the sample, right? So it turns out a correct algorithm would be to flip a coin to decide whether to keep one of these, and the probability of k over n, if this is the nth element so far, this record I have is a keeper. If so, if I now randomly pick one of the k elements to delete and replace with this one, this will generate a random selection. Does everybody kind of see the basic idea? You may need a proof that this is really uniform and that every element is equally likely to be in here. But it should be clear that as n gets larger and larger, it gets rarer and rarer that you're going to want to keep that record. Okay? And that with the whole idea of dealing with stream data, there are a lot of these kind of sampling ideas that go into building so you can maintain quickly a smaller sample that is really random, okay, for you to do some kind of analysis on. Any questions? Yeah?
So you accepted all the three results, and then in the fourth one you flipped the coin.
Fourth one, I flipped the coin with probability 3 out of 4, I decided to keep it. If I kept it, I flipped a coin from a 3-sided coin and decided which slot it was going to go into and then replaced it. Does everybody see it? Once I've decided I've kept it, I've got to get rid of somebody else. And so maybe I'll put it here, right? And for the next one with a 3 out of 5 probability, I'm going to keep it. If I've decided I'm going to keep it, I've got to flip a coin from, a 3-sided coin to decide where to put it. Then whenever anybody, well, either when I run out of n or somebody says, Joe, give me a sample, okay? And then I output this to that guy, okay? Any questions about that?
Biased towards the later tweets, like something like that, because
Is this biased towards the later ones? The answer is no, because if you look at it, the probability that we're going to keep each element is going to decrease with time. That's kind of the interesting thing.
It is biased towards the start actually. If you take like first 3, they are certainly there.
If you're saying, am I biased towards the start? The answer is no. Recognize that these 3 elements are sitting ducks for every other element that I decide to add, right? There was a 3/4 probability that one of these guys was going to go away here. There's a 3/5 probability that one of these guys is going to go away there. You see what happens? So this algorithm balances what we would like. The probability of including a new element is basically k over n. When n is very large, the odds we're going to include that record is very small, right? And the early ones have at least a moment in the sample, but they're going to be constantly shot at. And by the, for this record to have survived, it's going to have to have been shot at every single time. Okay? And, I mean, not end time, some fraction of those end times will actually be bullets, a chance of removing it. But it's got to either have very few times will the k over n thing, random number, happen to come up.
After a certain number of samples, this will kind of become steady, right? Because the probability of something to change would become very low. So,
you're saying after a while it's going to become low. Well, what is true is that what's the likelihood? Let's think about it. Halfway through the stream, assuming this is a random sample, halfway through the stream, how many of these guys are going to get into this final sample? You say about k over 2. Does everybody kind of see that? If this is truly a random sample that's uniform, which I'm claiming, what does random sample mean? It means that when I looked at these, half of these guys should be from the second half, and half of them should be from the first half. Okay? And I claim that that's going to happen, right? There's a 1 in, if you had 1 million records, there was a 1 in 1 million chance, that a 3 in 1 million chance that this record was going to come up, right? Which sounds small, but, if you're only getting it at 3 out of 1 million, what should the chances it be included be? 3 out of 1 million, right?
You have 500,000 shots in the second half, right? So, even if the odds are 3 out of 1 million, over 500.
So this guy, once this guy is in here, okay, well, let's think about it. 3 over 1 million a chance of getting in. What's the expected number? Let's think about it. Let's say we only had 1. Let's make it, because it's easier to analyze. What if k is equal to 1? Okay? What is the likelihood? There's a 1.5 million chance here. Does everybody kind of agree that this element's going in? And a 1 in almost a half million. There's a 1 in 1 million chance the last one is going in. How many shots will these guys, what's the probability that any of these guys are going to get in? Okay? There's a 500,000 elements. 1 in a 500,000, a 500,000 times 1 over a 500,000 means the expected number of shots coming in here is going to be between 1 or 2. Do people kind of see what I'm saying now? Think about, let's just say we were playing the game where there were 1 million items. There's 1 target here, right? How many times is this thing going to be replaced? That's really, I guess, the question you're asking, right? Well, you could compute by using a binomial distribution what's the probability that how many replacements there'll be and stuff like that. But just as an arm thing, what's the expected number of replacements? The probability of this getting replaced here is getting in there is 1 in 500,000, right? The probability of getting in here is 1 in 1 million, right? If we sum up 1 over 500,000, 500,000, and we did that 500,000 times, that would be an expected number of change of which is 1, right? If it was out of 1 million, the expected number of changes would be a half, right? So there is something less than a 1/2, the expected number of changes is less than 1 between all these elements at the end, which is pretty much what you would expect. Does everybody kind of see that? So it does what I'm looking at this room, the people need to compact a little bit. Any questions from this side? Okay. So anyway, recognize that one of the sampling problems people have to deal with are these stream sampling problems, okay? And that there are clever algorithms for randomly sampling from big streams rather than saying, oh, I've got to get it all, I've got to store it and then sample it. Any questions?
So in that, if we talk about the first 500,000, right? So let's
Yeah.
say we talk about the second or third element.
Yeah.
So the probability of this third element being picked up would be 1 by 3.
The probability of this one getting picked up would have been 1 by 3. The probability that it's eventually going to get discarded is much greater. Okay? You know, so if you think about it, how many, let's think about it. If we only have one of these things, how many times, what's the expected number of times this thing's going to get discarded? Okay? I claim that that the first element is obviously going to get in there. There is a 1/2 chance it's going to get discarded in the next round, right? If it doesn't, there's a 1/3 plus 1/4. This now is, I think, gets above 1/2. Okay? If you look at it, how many rounds do you need to go until the sum of the probabilities you get discarded equals 1/2? It turns out it's something like doubling. We could sit down and prove this thing, but if you take a look at what is the sum of I as it goes from x to, you know, until the sum of 1 over I is greater than or equal to 1/2. Okay? Basically, you've got to double your range down to get that probability to be very high. Okay? So basically, in general, this one is going to get tossed on average about log n times. You're going to overthrow the king about log n times in the course of this kind of a computation. Okay? Again, occasionally he's going to survive. 1 out of every 1,000,000 times he would survive. Okay? But he'd be sweating the entire time. Okay? Any questions? Okay? Okay. Any questions about how this works? It's an interesting topic. Any questions? Okay, good. Okay, the other thing which I'm going to talk about fairly briefly, okay, is I did want to talk a little bit about how parallel, you know, again, what I consider to be the definition of big data is it's one where you need more than one computer to analyze it. This is my gross definition. And, you know, that when we start looking at parallel processing or distributed processing, when I was growing up as a young graduate student and stuff like that, people didn't talk about distributed computing. Distributed computing I think of as computing across many machines over a network. People used to talk about parallel computing where they had these very complicated beasts with, 16 CPUs or something like that. And even now when you go to the people who do numerical computation, they have, fairly tight machines with, with millions of processors on it. Okay? But the way I think about it is parallel processing is something that happens on one machine. Okay? Distributed processing is what happens on many machines over some kind of a network. And, one of the trends that has made big data possible has been sort of the advent of distributed processing. It has become harder and harder to build a big machine with a large amount of, processors and things like that. It has become, however, much cheaper to have a network or a data center full of different servers, full of different machines, and have them talk to each other over a network. And this is the way the kind of big data processing that we deal with typically is done on distributed computers. Any question? One of the issues with this kind of processing is that, again, what typically happens is there's a cost of communication, of moving data from one machine to another. There's a cost of actually computing something. And, the advent of, in the olden days, people worried about how many multiplications were happening on a process. These days, often in big data kind of jobs, the bigger cost is how much data movement there is. And, what ends up making, being the easiest thing to parallelize are jobs that don't communicate very much. Any questions? That should be clear. So when I think about, let's say, trying to use either a network of machines or perhaps even multiple cores on a machine, the easiest way to exploit parallelism, which happens in big data a lot, has to do with partitioning. If I could take my data and what you call it, and partition it, okay, into disjoint groups. Often I can compute a model on each group independently, okay? I can do the analysis on completely independently, and maybe combine them at the end, okay? If you think about what happens on k-means, suppose we wanted to have a k-means algorithm parallelized. Does everybody remember what k-means clustering was? What were the two phases, let's say, of k-means, and how would we do it? Suppose I had a huge, huge amount of points to be clustered, okay? And I wanted to do this on multiple machines. How would I go about doing that? Okay, you could imagine probably partitioning the data, okay? Okay? But what has to happen in k-means? Does anyone remember? What? First I have to pick a centroid. So typically k is much, much less than n here, right? So n is big. If k is small, I have to have k centroids. Does everybody see that? And then I've got to do what? Point to centroid type of thing. How would I do this in a parallel way? Okay? If we think about it, what would happen to do k-means in a parallel way? What would I want to do? If I gave each machine a chunk of the data, okay? If I have, let's say m machines, if I gave each machine n over m of the data, how would I parallelize it? Okay, this computation.
We just swap the data, like after one is done with that, we just do it to other machines like that. So.
Okay.
Well, you can't just do nearest neighbor on each and then say,
Well, if k is small, how might I do it? Let's think about this. Maybe what I would do is somehow start out, pick the first k of these guys as my centroid, okay? If I send the centroids out to everybody, centroids are fairly small. Is that right? Each centroid is small. If I want 100 clusters on this thing, does everybody agree that that's a small amount of data to move around, right? Now, to ask each one of these points which is its nearest neighbor of these k, I could certainly go and compute that. Does everybody see that? And I could do that independent of all of these, right? Could I compute the centroid of each of the points on each machine? So let's see. So first I gave it the first round is I give the current centroids to everything. Does everybody agree that I could, if I give everybody the centroids, I can scan, each machine can scan independently to decide which of their points have which of the centroids as their nearest neighbor. Does everybody agree with that? Now that I know I've got all of these points here as my nearest neighbor, okay, I want to recompute centroids. Does everybody see that? Yes. How should I do this? Okay, I could ship all the points, say this is going to be my k equals 1 machine, and send all the points that were nearest to 1 over to here. But that seems very wasteful, doesn't it? That seems to involve a lot of movement. What might I do? Does everybody see I could compute the centroid of all of these things and pass that around, and the centroid is a much smaller thing, right? And if I knew what the centroid was and I knew how many points there were, does everybody see that now each one of these machines I'm going to have k new centroids and a frequency for each one of them? And I claim if I pass this much smaller amount of data to one place, I could compute the new centroids. Does everybody kind of see that?
doesn't centroid depend on the points that it doesn't have in that machine? So, what's that machine? Is that m equals 1, the top one?
Yeah.
So, like, if you're computing a new centroid, but you don't have all the points that are nearest to that centroid.
Okay, what I'm going to do is I'm going to pass my 10, I start out with k initials points as centroids. Let's say I'm going to have one server that's going to be in control of everything, right? It picks, says, goes to the first machine, say, give me your K first points. Okay, fine. I'm going to make that be my initial centroid, right? I'm now going to send those K points to all the other machines, saying these are now the centroids for your cluster. Does everybody see that? I now say you go and figure out how close all of your points are to each one of the centroids. Right? Now, what I get from here are K new centroids. The centroids of the closest points to each of these. If I pass that information back to my master, and all of them pass it back to their master, can they compute an updated value of what the center is? I guess. Well, I mean, the answer is either I guess or you see it, okay? So kind of, what am I saying? Suppose, let's say on the first machine, there were 3 points that had its nearest neighbor of 1. On the second machine, there were 5 points that had its nearest neighbor of 1. On the third machine, there were 10 points that had its nearest neighbor of 1. Right? This machine could compute the centroid of these 3 points. This machine would compute the centroid of these 5 points. This would compute the centroid of those 10 points. If we sent this back to the new machine, what is the centroid of those 18 points?
That's what I wasn't clear to me that you could do.
Okay, well, what I claim it would be is this centroid would deserve 10/18ths of the weight. This centroid would observe 5/18ths of the weight. This would be 3/18ths of the weight. Does everybody see that? That should now be believable. Okay? And so by passing the centroids around, you can kind of do this kind of computation, okay, leaving the vast bulk of the points intact. That's kind of the important point here. Does everybody see that?
Yes.
Any questions about that? Okay? Fair enough. So you're best off, the kind of problems that work out well are when you can divide your data up and do your computations separately on the data and combine them at the end. Any questions? Okay. So when I think of a distributed processing thing, you know, you used to hear about primitive cultures that when you asked them that didn't know much about numbers, how did they know how to count? They knew 1, 2, many. They didn't have a word for 3. Okay? To a certain extent, I think that the same thing is true with distributed processing. That I'm going to claim that there's kind of like 3 different classes of distributed applications you need to worry about. One is one where you're only using your machine. And if so, this is simple. You guys know how to use your machine. Maybe you're going to do something to try to keep the cores of the multiple cores on your box busy, but there's a limit to how complex that is. When you have a small number of machines, maybe you can have as the pilot of this thing can keep an eye on what's running on each machine and combine them manually or with a script or something like that. But when you are computing on a very, very large scale, you need to have some kind of a system that is going to be maintaining the reliability and the communications and dealing with the special cases associated with many, many things. One thing that I can say, this semester I'm teaching 2 classes. I may have had a haggard look all semester, tired, worn down, and the reason is because I'm teaching 2 classes, and one of them is very large. One of them is 50% larger than any other class I've ever taught before. Now, why is that wearing me down? Okay? You may say, I'm just talking to you people. It's not any difference how many people are filling the room. And on one level, that's right. But what is it that happens when you have, as things scale, is you get more and more exceptions and weird cases. Does everybody kind of get that idea? That the weirdest thing that is going to happen is going to be more weird than before, right? How many of you are going to have a dog eat your homework? Well, very few of you. But if the class scales large enough, will someone in the class have a dog eat their homework? Yes. Okay? And the same kind of philosophy is true in, you know, is kind of, I'm going to talk about why do people use these systems like Hadoop and, you know, for managing things. A lot of the issue with managing things of scale are that things become, exceptional things happen when you increase the scale of something large enough. So I wanted to think like if I was thinking about a social gathering of how many people that you were arranging, okay? You know, for one person, it's easy for you to figure out what to do. With a couple of people, you can make phone calls, you can deal with it, okay? If anybody ever try to arrange a dinner with 10 people at the dinner, and what happens? The only way it works is if one person is the leader. Is that correct? Okay. Has anybody ever performed a wedding or something like that where they needed to, you know, you don't take, you know, you have a fixed menu now. Why do you have a fixed menu? Because it's much too complicated. Communication costs of dealing with different requests are too many things. If you're at an event with 1,000 people, have you ever been in an academic, what event of 1,000 people? A wedding. Okay, and what fraction of it, when you're at a wedding of 1,000 people, what fraction of them will the bride and groom know? You say 1%, okay, I'd like to think more than 1%, but I will say less than 20% is probably right, okay? And that's sort of true, right? When you have an event for 10,000 people, like a major conference or something like that, recognize that you can't hold it in most cities because there aren't enough hotel rooms to have 10,000 people come in. So you see that? Even that's the kind of thing you worry about. I once organized a conference and I saw the manual that this big academic society had for hosting conferences. And one thing that they had in there that impressed me was that if the conference had like 30,000 people or more, they had to have a contingency plan in case one of the attendees would die. Okay? And the reason being, if you have 100,000 people at an event, somebody will die during the event. Okay? Is that clear? If you live to be 100 years old, how many days will you live? 36,000 days. Okay? So what is that? 100,000 days. If it's a one-day event, that's 3 lifetimes worth of people, right? And somebody's going to go that day, okay? Any questions about it? So maybe look around a football stadium. One of those people in the crowds did not make it home, okay? Is basically true, okay? So it's recognize that probabilities of failure increase dramatically as you have as n scales. And so one of the things that made distributed processing work was that there started being systems around that would coordinate the use of multiple